Our universe might be running on faulty software. I am talking about real, measurable glitches in physics that suggest we live in a simulation. This journey will give you a new framework to understand everything from the bizarre rules of quantum mechanics to the vast silence of outer space. Why do particles change behavior when we look at them? What if the cosmic silence is not an accident, but a design feature? By the end, you will see the fabric of reality in a completely different light. What does it mean if our world is not base reality, but a sophisticated construct? The first and perhaps most famous glitch in our reality is a simple experiment with a profound mystery at its core. It begins with a barrier, two thin slits cut into it, and a beam of particles, say electrons or photons of light, aimed at that barrier. When no one is watching, when no instrument is trying to see which slit each particle goes through, something beautiful and strange happens. Each particle does not simply go through one slit or the other. Instead, it behaves as if it is a wave, passing through both slits simultaneously and interfering with itself on the other side, creating a striped pattern of light and dark bands on a detector screen. This is the signature of wave behavior, but the moment we place a measuring device to observe which specific slit the particle travels through, the magic stops. The interference pattern vanishes. The particle now acts like a single, solid object, going through one slit or the other and leaving two simple clumps on the screen. It is as if the particle knows it is being watched and changes its behavior to suit our expectations. This is the double-slit experiment's observer effect, a cornerstone of quantum mechanics that feels less like a law of nature and more like a programming quirk. The physicist John Wheeler framed this in a deeply philosophical way, asking if the universe requires a participant to bring it into being. In his view, our act of observation, of measurement, is what collapses a haze of possibilities into a single, solid fact. Think of it like a vast, open-world video game. The entire landscape is not rendered in perfect detail all at once. That would require impossible processing power. Instead, the game engine only loads the high-resolution textures and complex physics for the area right in front of your character. Everything else remains in a fuzzy, low-detail state of potential. Is our universe doing the same? Does the simulation only bother to calculate the definite position of a particle when an observer, a conscious player within the system, looks at it? This glitch suggests that reality may not be a fixed stage, but a dynamic performance that only fully materializes under the spotlight of attention. It forces us to confront a dizzying question: what or who ultimately counts as an observer in this cosmic game? This uncanny awareness of being observed is not the only strange rule in our cosmic operating system. The very laws of physics themselves seem suspiciously fine-tuned for our existence, as if someone set the dials just right before hitting start. Think of the fundamental forces that govern our universe, like gravity and the strong nuclear force that holds atoms together. Their strengths are not arbitrary numbers, they are precise values. If gravity were even slightly stronger, the universe would have collapsed back on itself immediately after the Big Bang. If it were slightly weaker, stars and galaxies could never have formed from the cosmic dust. The strong nuclear force is just as delicately balanced. A fraction of a % difference would mean hydrogen could not fuse into helium, and the furnaces of every star would have remained cold and dark. This perfect calibration extends to dozens of other constants, from the mass of an electron to the rate of the universe's expansion. The odds of all these numbers aligning by pure chance to create a universe capable of hosting planets, chemistry, and conscious life are astronomically small. This cosmic coincidence is known as the Anthropic Principle, the idea that we observe a universe suitable for life because we are here to observe it. But to many physicists, that answer feels like a tautology, a logical circle that avoids the deeper mystery. Experts like Paul Davies have argued this fine-tuning demands a real explanation beyond mere luck. It feels less like a random accident and more like a programmer carefully setting the initial parameters for a stable virtual environment. In a simulation, the rules are pre-coded, chosen from the start to allow for complexity to emerge within the system. This raises a profound possibility that our universe's laws were intentionally designed or selected. Are we living inside a crafted experiment, a universe built with purpose? Or are we simply one lucky bubble in an infinite multiverse, a cosmic lottery winner where all the numbers just happen to come up life? The fine-tuning of reality is a silent, mathematical glitch that whispers of intention behind the equations, making the cosmos feel less like a wilderness and more like a carefully tended garden. But this fine-tuning of cosmic constants is not the only place where our reality feels suspiciously designed. There is another, even more direct glitch in the system, one so bizarre that even Albert Einstein found it deeply unsettling. He called it spooky action at a distance. Today, we know it as quantum entanglement. The concept is simple to state but impossible to visualize with our everyday logic. Imagine two particles, perhaps a pair of electrons, created together so that their properties are linked. You then separate them, sending one to a lab on Earth and the other to a detector near a distant star. According to all classical physics, they are now independent objects, but quantum mechanics reveals they are not. When you measure a property of the particle on Earth, say its spin, the result is random. Yet, at that exact instant, the particle near the star instantly assumes the opposite spin, no matter how many light years away it is. This connection appears to happen faster than light, violating a fundamental rule Einstein himself established. This is not a theoretical idea. It has been confirmed in countless rigorous experiments. The particles seem to share information instantaneously, as if distance is irrelevant to them. From a simulation perspective, this spooky action makes perfect sense. Think of two characters in a massively multiplayer online game. They might appear to be on opposite sides of the virtual continent, separated by vast digital landscapes. But if they are linked by a shared quest or a common inventory, their connection is not mediated by traveling across the game world. Instead, the game's central server, the underlying code, simply updates their status simultaneously in its database. The characters are not communicating across space. The space itself is just a rendered illusion for the player's benefit. The real connection exists on a deeper, non-spatial layer. Quantum entanglement could be a signature of this kind of underlying architecture. The entangled particles are not sending a signal. They are simply two access points to the same piece of data in the simulation's code. Their apparent separation in space and time is an emergent property, a feature of the rendered world we experience, not the fundamental reality of the system running it. This glitch suggests that locality, the idea that objects are only influenced by their immediate surroundings, might be an illusion. It pushes us to ask what the true framework of our universe really is, if not the stage of space and time we perceive. This idea of an underlying code brings us to the very edge of what we can measure, to a place where space and time themselves seem to pixelate. There appears to be a fundamental limit to how small things can get in our universe, a shortest possible distance known as the Planck Length. To grasp its scale, think of comparing a single atom to our entire solar system. That is the kind of immense gap we are talking about. The Planck length is so vanishingly small that it defies our everyday intuition, roughly 1.6 times 10 to the negative 35 meters. According to our current laws of physics, trying to probe distances smaller than this does not just become difficult, it becomes meaningless. The concepts of here and there, of before and after, simply break down. This is not just a technological barrier, it is a theoretical wall built into the fabric of reality. The physicist Max Planck, for whom this scale is named, first stumbled upon it while studying black body radiation, and it has since emerged as a fundamental constant in quantum gravity. It suggests that space is not a smooth, continuous canvas as Einstein described, but might instead be grainy or discrete at its most fundamental level. This is where the simulation hypothesis offers a compelling analogy. Think of a digital photograph on your screen. From a distance, it looks perfectly smooth and continuous. But if you zoom in far enough, you eventually see the individual pixels, the tiny squares of color that are the smallest units of the image. You cannot zoom in further than a pixel. There is simply no more information there. The Planck length could be the cosmic equivalent of that pixel. It might represent the fundamental resolution of our universe, the smallest possible step in the simulation's coordinate system. If reality were a continuous, infinitely divisible thing, simulating it would require infinite computational power to track every single possible point. But if reality is pixelated, if it has a finite information density, then it becomes computationally feasible. The existence of a Planck scale could be a telltale sign of a rendering constraint, a built-in limit that prevents the simulation from having to calculate an impossible infinity of detail. It hints that when we probe the deepest foundations of spacetime, we are not looking at nature's bedrock, but at the resolution limit of the display. This pixelated limit to reality leads us to a question that is at once philosophical and statistical. If our universe has the hallmarks of a construct, then who or what could have built it? The philosopher Nick Bostrom offered a startling answer framed not by physics, but by pure probability. He began with a simple assumption that a sufficiently advanced civilization would eventually gain the ability to create vast, detailed simulations of conscious beings within their own history. These would not be simple games, but entire worlds as rich and complex as our own, populated by simulated minds that believe they are real. Given enough time and computational power, such a civilization might run not just one, but millions or even billions of these ancestor simulations. Now follow the numbers. If that is true, then the total number of simulated minds in existence would vastly, overwhelmingly outnumber the minds in the original, base reality. Statistically speaking, any conscious being, like you or me, is far more likely to be one of those simulated minds than one of the original biological ancestors. Bostrom's simulation argument presents this not as proof, but as a stark logical possibility. If the premise is true that such simulations are possible, then the conclusion is almost inescapable. We are probably living in one. This glitch uses the cold math of probability to challenge our most basic existential assumption. It reframes our entire civilization, with all its triumphs and hardships, its art and science, as potential data points in a grand computational experiment run by a higher order of intelligence. The purpose could be academic, a way to study historical paths, or perhaps even recreational, a form of entertainment or storytelling on a cosmic scale. This argument forces us to consider our place in a potential hierarchy of realities. Are we the creators or are we the created? Are our struggles and joys the primary narrative, or are they merely one thread in an infinite tapestry of simulated experiences? The simulation argument does not tell us that we are in a simulation. It tells us that we should seriously consider the odds, and in doing so, it transforms the universe from a singular stage into one of countless possible renderings, where the line between reality and illusion is drawn not by physics alone, but by the sheer weight of statistical likelihood. Yet the most profound evidence of an underlying code may not be in the quantum realm, but in the breathtaking beauty of our own world. Look closely at a head of broccoli, tracing the curve of its florets. Follow the branching veins of a river delta from a satellite's view, or watch the swirling eddies of a storm cloud on a weather map, you will see the same patterns repeating at different scales, a kind of cosmic echo where the shape of the whole is mirrored in its tiniest parts. These are fractals, and their presence throughout nature is a sixth, deeply elegant glitch in our reality. The mathematician Benoit Mandelbrot gave us the language to describe this phenomenon. He showed how a strikingly simple mathematical equation, when iterated over and over, could generate a shape of infinite complexity, the now famous Mandelbrot set. Zoom into its boundary forever, and you will never find a smooth edge, only an endless cascade of swirling, self-similar structures, each a miniature reflection of the whole. This is not just a mathematical curiosity, it is a blueprint. The same recursive logic that builds the Mandelbrot set seems to be at work in the branching of trees, the contours of coastlines, and the distribution of galaxies across the cosmos. Why would the physical universe, born from a chaotic explosion, organize itself according to these pristine mathematical rules? It suggests an underlying algorithmic process, as if nature is not building things from scratch but running a simple, efficient program that reuses the same elegant subroutine to generate complexity at every level. Think of it like a video game developer creating a vast forest. They do not manually model every single leaf and branch. Instead, they write a generative algorithm, a set of rules that says, start with a trunk, split into branches, split those branches again, and apply a texture. One piece of code, repeated recursively, creates an entire, believable ecosystem. The fractal patterns we see everywhere could be the signature of a similar kind of cosmic coding. The universe appears to be using a set of elegant, recursive algorithms to build itself, maximizing beauty and complexity from minimal instructions. This glitch moves us from the cold probabilities of simulation arguments to something more artistic. It implies that the stunning diversity of our world, from snowflakes to spiral galaxies, might not be accidental. It could be the natural, even inevitable, output of a simulated environment's generative rules. We are not just living in a possible simulation, we might be living inside a breathtakingly beautiful piece of mathematical art, its patterns a subtle whisper of the programmer's hand. Even the most elegant code can contain a fatal error, a paradox where two core rules of the system contradict each other completely. This is the heart of the seventh glitch, a conflict so deep it threatens to unravel our understanding of reality itself. It happens at the edge of a black hole, a place where the laws of physics as we know them break down. According to Einstein's general relativity, a black hole is the ultimate cosmic eraser. Its gravity is so intense that nothing, not even light, can escape its pull past a boundary called the event horizon. If you were to throw a book, a hard drive, or any object containing information into a black hole, relativity tells us that information is gone forever, swallowed and lost to the universe. It is as if the data has been deleted from the cosmic hard drive, but quantum mechanics, the rulebook for the very small, insists this cannot happen. One of its most sacred principles is that information is never truly destroyed. It may be scrambled, transformed, or rendered incredibly difficult to read, but it must be preserved in some form. You cannot just delete the universe's data. So which is it? Is information permanently lost in the black hole's depths, or is it somehow preserved? This is the black hole information paradox, a puzzle that Stephen Hawking wrestled with for decades. He initially believed the information was indeed lost, which would mean quantum mechanics was fundamentally wrong. But the implications of that were so severe it suggested a deep inconsistency, a bug in the operating system of our cosmos. From a simulation perspective, this paradox feels eerily familiar. It is like a critical software conflict. Imagine two essential programs running on the same computer, one handling graphics and the other handling data storage. The graphics program, like general relativity, says that when an object falls into a special zone, it should be removed from the render entirely, deleted to save resources. But the data management program, like quantum mechanics, has a strict rule that no user data can ever be permanently erased. The system crashes because it cannot obey both commands at once. Our universe seems to be facing a similar crash at the edge of a black hole. To resolve this, some physicists have proposed a radical solution, the holographic principle. This idea suggests that all the information about everything that falls into a three-dimensional black hole is not lost inside it. Instead, it is perfectly encoded and preserved on the black hole's two-dimensional surface, its event horizon. Think of it like an incredibly advanced piece of data storage. The three-dimensional objects we see falling in are like the rich, immersive experience of a hologram. But the actual data that creates that experience is stored on a flat, two-dimensional surface, like the security image on your credit card. The three-dimensional reality is a projection, an illusion generated from information written on a boundary. This glitch points to a staggering possibility that our entire three-dimensional universe, with all its galaxies, stars, and planets, might itself be a holographic projection from information stored on a two-dimensional surface at the cosmic horizon. It hints that the world we experience is not the fundamental reality, but a rendered output, a simulation where data is managed on a layer we cannot perceive. The black hole information paradox is not just a theoretical headache. It is a direct signal that our reality might have a layered architecture, with information stored somewhere else entirely, waiting to be decoded. A random brain floating in the void is more likely than the world you know. This unsettling idea is not science fiction, but a serious philosophical glitch known as the Boltzmann brain paradox. It emerges from a simple, chilling premise. If our universe is ultimately headed toward a state of maximum entropy, a featureless soup of particles in perfect, random disorder, then given enough time, sheer chance could cause those particles to momentarily arrange themselves into any configuration, including the configuration of a fully formed, conscious brain, complete with a lifetime of detailed but entirely false memories of a past that never happened. In a truly eternal and chaotic cosmos, such fleeting, self-aware fluctuations should statistically outnumber the rare, sustained islands of order like our entire universe with its billions of years of consistent history. Yet here we are, perceiving a vast, structured cosmos with a coherent past. Why do we find ourselves in a grand, ordered narrative and not as a momentary accident of chaos? This paradox, rooted in the work of physicist Ludwig Boltzmann, suggests something is deeply off with our assumptions. It implies our reality may not be a random, eternal accident, but something with a definite beginning and stable rules. From a simulation perspective, this glitch makes perfect sense. A simulation is not a random system. It is a structured program with initial conditions and consistent laws designed to generate a coherent story for its inhabitants. It actively prevents the kind of nonsensical, random fluctuations that would break the narrative. Think of a vast, immersive video game. The game world is built with internal consistency. Its history is logged, its physics are reliable. The system would not randomly generate a fully aware character with memories of events that never occurred within the game's own timeline. That would be a catastrophic bug, breaking immersion and functionality. The simulation ensures stability to maintain the integrity of the experience. The fact that we do not observe Boltzmann brains, that we instead perceive a universe with a clear arrow of time and a reliable past, could be a sign that our reality is similarly architected, artificially stabilized to avoid narrative chaos. This leads us to a profound and personal question. How much can we trust our own memories and the story of our cosmos? The Boltzmann brain paradox does not prove we are simulated, but it highlights how strangely unlikely our orderly existence is within a purely random, eternal framework. It suggests the cosmos we experience might be curated, its consistency not a lucky accident, but a fundamental feature of its design. But this strange orderliness of our universe is not just felt, it is written down in a language we somehow learn to speak. The ninth glitch is not a physical phenomenon, but a philosophical one, the unreasonable effectiveness of mathematics. Why do the abstract equations dreamed up by humans, often with no practical intent, later turn out to be the perfect keys to unlock the deepest secrets of nature? A physicist named Eugene Wigner famously pondered this mystery. He marveled that a mathematical concept created for pure intellectual play could later describe the orbit of a planet or the spin of an electron with uncanny, almost spooky precision. It is as if we are discovering a user manual for reality that was written in a language we just happened to invent. This goes far beyond simple measurement. The complex number I, the square root of -1, was long considered a beautiful but useless abstraction. Then it became the cornerstone of quantum mechanics, essential for describing how the subatomic world actually works. The geometry of curved spaces, explored by mathematicians like Riemann decades earlier, provided the perfect framework for Einstein's theory of gravity. Time and again, the universe seems to be running on a logic that our mathematics is uniquely suited to decode. This eerie alignment suggests something profound. Mathematics may not be merely a human invention for describing the world. It might be the native programming language in which the world is actually written. When we do physics, we are not just observing nature, we might be reverse engineering the simulation source code. Our most brilliant theoretical breakthroughs could be moments where we successfully decompile a small piece of the cosmic operating system. This glitch creates a fascinating loop between mind and cosmos. It implies that the human capacity for abstract, logical thought is not an accidental byproduct of evolution in this universe, but a feature that aligns us with its fundamental architecture. Our minds seem tuned to understand the algorithms of existence, as if we are both the players in the game and, in a limited but growing way, the programmers beginning to understand its syntax. The unreasonable effectiveness of mathematics whispers that the boundary between the thinker and the world is thinner than we ever imagined, that in tracing the elegant lines of an equation, we might be glimpsing the very blueprint of our own reality. The universe's profound silence might be its most unsettling feature. With hundreds of billions of stars in our galaxy alone, and many of those hosting Earth-like planets in their habitable zones, the cosmos should be teeming with life. The mathematics of probability screams that we should not be alone. Yet when we point our telescopes and listen with our most sensitive instruments, we hear nothing but the ancient, natural static of stars and gas. This eerie quiet is the heart of the Fermi Paradox, named for the physicist Enrico Fermi who, over a casual lunch, posed the deceptively simple question, where is everybody? If life is a natural cosmic process, the galaxy should have been colonized many times over by now. We should see the signs, the megastructures, the energy signatures, the radio chatter of other civilizations. But the sky remains silent. This is not merely an absence of evidence, it is a profound contradiction between expectation and observation. One compelling resolution to this paradox emerges directly from the simulation hypothesis. In a vast, resource-intensive simulation, rendering every single planet with a complex, evolving civilization would be an extraordinary computational burden. It would be like a video game developer trying to populate every single planet in a galaxy-sized map with unique, fully realized cultures and histories. The processing power required would be unimaginable. It is far more efficient to have only one active player or one focal point of conscious observation. The rest of the cosmos can be rendered in low resolution as beautiful but empty backdrops, filled with the potential for life but not the actual processing heavy reality of it. Our cosmic loneliness, then, might not be a tragedy of distance but a sign of optimization. We are the characters in the story the simulation is telling, and the empty universe is the stage, carefully crafted to feel vast and real without the need to simulate other audiences. Another possibility is even more introspective. Perhaps we are not alone but isolated by design. If this is a constructed reality for study or education, contact with other civilizations could be a variable that is deliberately controlled or turned off entirely to observe how a single intelligent species develops without external influence. It is the ultimate controlled experiment. Or the truth could be stranger still, that advanced civilizations do exist, but in forms or dimensions that are simply not rendered for our level of perception, like non-player characters in a game that are invisible to us because our character has not unlocked the required ability to see them. The Fermi Paradox transforms from a puzzle about aliens into a glitch about the nature of our reality. The silence is not an accident, it is a clue. It suggests that the universe we perceive is curated, its emptiness a deliberate feature forcing us to ask if we are truly the only players in this game, or merely the only ones currently being rendered by the system. Quantum mechanics presents us with a world that remains stubbornly unresolved until we look at it. A particle like an electron does not have a definite position or spin until it is measured, existing instead in a haze of all possible states at once, a condition known as a superposition. The moment we observe it, this cloud of potential collapses into a single, concrete fact. This is the measurement problem, and it is the 11th glitch in our reality. The deep mystery is not that this happens, but how. What exactly constitutes a measurement? Is it the click of a detector, the interaction with a photon, or does it require a conscious observer to finally make things real? Our most successful theory simply states that the math changes when a measurement occurs, but it offers no physical mechanism for the collapse itself. It is as if the rulebook has a glaring blank space where the most important instruction should be. This has led to a spectrum of interpretations, each trying to fill that void. The Copenhagen interpretation, the traditional view, essentially says the wave function collapse is a fundamental, inexplicable act, a boundary between the quantum world and our classical one. The many worlds interpretation takes a radically different approach, proposing that the wave function never collapses at all. Instead, every possible outcome of a quantum event actually occurs, splitting our universe into an ever-branching tree of parallel realities. While mathematically elegant, this idea asks us to accept an infinity of unseen worlds. Both of these and other interpretations feel like workarounds for a feature of reality we do not fully understand. From a simulation perspective, however, this glitch feels less like a bug and more like a clever optimization technique known as lazy evaluation. In computer science, lazy evaluation means a system does not perform a complex calculation until the result is absolutely needed. Think of a vast open-world game. The entire city is not simulated in real time down to the flight path of every single pigeon. Those details are only calculated and rendered when the player turns their camera to look at them. Until that moment, the pigeon exists only as a placeholder, a probability. Our universe might operate on a similar principle. The electron in its superposition is not in a specific place because the simulation has not yet bothered to calculate where it is. That expensive computation is deferred until an observer, a conscious player within the system, accesses that information. At that point, the system quickly resolves the probability, picks an outcome consistent with the quantum rules, and renders it as reality. This would explain why there is no physical mechanism for collapse within the world, because the collapse is not happening in the world, it is happening in the layer of code that manages the world. The measurement problem thus challenges our deepest notions of causality and existence. It suggests that the solid, definite universe we experience is not a pre-recorded film, but an interactive rendering generated moment by moment in response to our attention. We are not passive spectators on a fixed stage, We are participants whose very act of looking calls the world into being from a sea of potential. Time itself feels like the most solid feature of our world, yet it hides a deep asymmetry. We remember the past but not the future. We see eggs shatter and never reassemble, cups of coffee cooling to room temperature, never spontaneously reheating. This relentless march from order to disorder is governed by the second law of thermodynamics, the increase of entropy. It gives us the arrow of time, the undeniable feeling that time flows in one direction. But here is the glitch: the fundamental equations of physics, from Newton's laws to Einstein's relativity to quantum mechanics, are perfectly symmetric in time. If you were to take a video of two planets orbiting each other or two particles colliding and play it backwards, the physics would still look perfectly valid. The equations do not care which way time flows, they work just as well in reverse. So why does our macroscopic experience of time have such a powerful one-way direction? The answer seems to lie not in the laws themselves, but in the starting conditions of our universe. Physicists like Sean Carroll point out that the early cosmos was in a state of extraordinarily low entropy, a condition of almost pristine order. It was like a room that started perfectly clean and organized, with every book on its shelf and every sock in its drawer. From that single, highly ordered starting point, the only possible statistical direction is toward greater mess and disorder. That initial state is the wound-up spring that drives the entire arrow of time. But this raises a profound question: why did the universe begin in such a special, low-entropy state? Statistically, a random, chaotic beginning is infinitely more likely. It is as if the cosmic deck was stacked from the very first moment. From a simulation perspective, this is not a mystery, it is a design choice. When a programmer initializes a complex simulation, they do not start it in a state of maximum chaos and noise. They start it with a clean, orderly set of initial parameters, a stable platform from which the program can run and a coherent narrative can unfold. The low-entropy beginning of our universe could be exactly that, the boot-up sequence for a cosmic simulation. The arrow of time, then, is not a fundamental law written into the code, but an emergent property that arises from those carefully chosen initial conditions. It is the simulation's way of creating a linear, causal story that we can experience, remember, and make sense of. Without this built-in direction, events could happen in any order, cause and effect would unravel, and no consistent history could form. The one-way flow of time might be the ultimate narrative device, a feature that allows for memory, learning, and the very possibility of a story to be told within the construct. This glitch makes us question the nature of our own temporal experience. Is the past truly fixed, or is it simply a log file that we are reading as we move forward through the runtime? Is the future still being calculated, or is it already rendered, waiting for us to arrive? The arrow of time feels absolute, but it might be the most elegant and necessary illusion of them all. The feature that makes this simulated reality feel convincingly, irrevocably real. The solidity of empty space is an illusion. Even in a perfect vacuum devoid of all matter and light, the universe is not still. Quantum theory tells us that at the tiniest scales, empty space is a seething, bubbling sea of potential. Particles and their antiparticles spontaneously wink into existence, borrowing energy from the vacuum itself, only to annihilate each other and vanish an instant later. These are quantum fluctuations, and for decades they were considered a purely mathematical quirk, a strange prediction with no tangible effect on our world. Then, in 1948, a physicist named Hendrik Casimir predicted something astonishing. He calculated that if you placed two perfectly smooth, uncharged metal plates extremely close together in a vacuum, these ghostly quantum fluctuations would actually push the plates together. The reason is subtle yet profound. Between the plates, only certain wavelengths of these virtual particles can fit. like specific musical notes resonating in a tiny chamber. Outside the plates, all wavelengths are possible. This difference in pressure from the ceaseless activity of the vacuum creates a net force that draws the plates together. It seemed like an impossible idea, a force arising from nothing, but by the late 1990s, experiments had confirmed it. The Casimir Effect is real. We can literally measure the push of empty space. This is not a metaphor, it is a direct physical manifestation of quantum foam, proving that what we call nothing is in fact a dynamic, energetic medium. From a simulation perspective, this glitch is deeply revealing. A perfect, featureless void would be computationally simple, a blank slate requiring no processing power. But a vacuum teeming with virtual particles is a system in a state of constant, low-level activity. It is reminiscent of background processes running on a computer, tasks that are essential to the operating system's function, but mostly hidden from the user. These quantum fluctuations could be the background noise of the simulation itself, the hum of the processor as it maintains the framework of spacetime, calculating possibilities and managing the underlying fields that give rise to reality. The vacuum energy they represent might be the computational cost of keeping the simulation stage ready, the energy required to sustain the empty space that makes our material world possible. This forces us to reconsider the very nature of emptiness. Is the vacuum truly the absence of everything, or is it the most fundamental something, the active substrate from which all particles and forces emerge? The Casimir Effect suggests that even in its quietest state, the universe is never truly idle, hinting at a hidden layer of constant activity, a cosmic background program forever running behind the scenes of our perceived reality. Even the most perfect logical system contains a flaw it can never fix. In the early 20th century, a quiet logician named Gödel delivered a devastating blow to the dream of a complete and perfect mathematics. He proved with ironclad logic that in any consistent formal system complex enough to describe basic arithmetic, there will always be true statements that cannot be proven within the system itself. Think of it as a cage built from the rules of logic, a cage that can never fully contain the truth it tries to describe. There will always be truths that lie outside, forever unreachable by the very tools we use to seek them. This is the essence of Gödel's incompleteness theorems, and when we apply this lens to physics, the implications for our reality are staggering. Our quest for a theory of everything, a single set of equations that perfectly describes the cosmos, might be fundamentally doomed. The laws governing our universe could themselves form such a formal system, containing inherent gaps, truths about reality that are real and consequential but forever beyond the reach of our scientific proof. It is as if we are trying to understand a vast and intricate novel, but the author has deliberately written certain plot points in a language that does not exist within the story's own world. The characters can study the book forever, but some mysteries are sealed from the inside. This glitch suggests that the simulation, if that is what we are in, might be built on a logical foundation with intentional blind spots. These undecidable propositions would not be bugs but features, perhaps designed to prevent the system from being fully reverse-engineered, or to allow for elements of genuine freedom and unpredictability within the programmed framework. It challenges our deepest scientific ambition, the hope that with enough time and intelligence we could know everything. Gödel's work whispers that ultimate knowledge may be structurally impossible from our vantage point within the system. We might forever be explorers in a mansion of logic, discovering room after magnificent room, but always aware that some doors are locked with keys that do not exist in our dimension. This leads us to a humbling and profound question. If our reality has built-in limits to understanding, what does that say about the nature of the reality that contains it? Are we living inside a puzzle that was never meant to be fully solved? The hologram on your credit card is a flat, shimmering surface, yet it creates the illusion of a three-dimensional object floating in space. This everyday trick of light points toward one of the most radical ideas in modern physics, a glitch where the very dimensions of our reality might be an elegant illusion. This is the holographic principle, and it proposes something astonishing: that all the information contained within any volume of space, every star, every planet, every person inside it, can be perfectly encoded on its two-dimensional boundary, like data written on the surface of a bubble. Physicists like Gerard T. Hooft and Leonard Susskind developed this idea not from science fiction, but from the intense struggle to resolve the black hole information paradox. They found that the entropy, which is a measure of information of a black hole, is not proportional to its volume as you might expect, but to the area of its event horizon, its surface. This was a profound clue, suggesting that the three-dimensional world falling into the black hole could be described entirely by information painted on its two-dimensional edge. Extend this idea to the universe itself, and the implications are breathtaking. The room you are sitting in, with its depth and furniture and air, might not be fundamentally three-dimensional. It could be a projection, a holographic image generated from information stored on a distant, flat surface at the very edge of the cosmos. Your perception of volume and solidity would be a magnificent rendering, an experiential output for beings like us who are programmed to perceive in three dimensions. From a simulation standpoint, this is a masterstroke of data efficiency. Storing and processing information for a full three-dimensional universe in real time is computationally monstrous. But if the true data resides on a two-dimensional surface, the complexity drops exponentially. The three-dimensional world we navigate would then be a real-time projection, a visual and tactile interface generated from that compressed data. Think of a modern three-dimensional movie. The immersive experience you have in the theater is not coming from a three-dimensional film strip. It is generated from data on a flat, two-dimensional digital file. The projector and your glasses work together to create the convincing illusion of depth. The holographic principle suggests our universe operates on a similar, though infinitely more sophisticated, principle. This glitch forces a complete shift in perspective. We are encouraged to think of reality not as a collection of solid objects in space, but as an informational construct. What we call particles and forces might be secondary manifestations, the readout of a cosmic code written on a surface we cannot see. It means the most fundamental layer of existence might not be spacetime at all, but information itself, with our rich, three-dimensional lives being its most beautiful and convincing expression. Even the most familiar substance in our world holds secrets that defy simple logic. Take a pot of boiling water and a pot of cool water, place them both in a freezer, and under the right conditions, the hot one will turn to ice first. This is not a myth, it is a verified, perplexing phenomenon called the Mpemba Effect, named for the Tanzanian student, Erasto Mpemba, who insisted on investigating it after noticing the effect while making ice cream. Classical thermodynamics tells us this should not happen. Cooling an object requires removing heat, and a hotter object has more heat to remove, so it should always take longer to reach freezing. Yet, in practice, the reverse can occur. The exact reasons are still debated by physicists, involving complex factors like evaporation, convection currents, dissolved gases, and even the peculiar behavior of hydrogen bonds in water as it cools. It is as if water has a hidden set of instructions that only activate under specific, non-linear conditions. From the perspective of a simulated reality, this glitch feels less like an error and more like a fascinating quirk in the physics engine. In a complex video game, especially one built over time, certain interactions might not follow the most obvious or efficient rule. An object might bounce strangely off a particular surface, or a character might clip through a wall in a specific corner. These are not game-breaking bugs, but emergent oddities from the interplay of countless lines of code. The Mpemba effect could be a similar kind of emergent behavior, a place where the simulation's simplified models for heat transfer, fluid dynamics, and molecular bonding interact in an unexpected way, producing a result that feels counterintuitive to us, the players. It reminds us that our scientific models, however powerful, are still approximations of a deeper, more complex system. This glitch transforms an everyday kitchen observation into a profound clue. It suggests that even the most ordinary aspects of our world might contain Easter eggs, hidden behaviors that point to the underlying architecture. Why would reality have such quirks unless it was built with layers of code that sometimes interact in surprising ways? The Mpemba effect invites us to stay curious, to question the consistency of the natural laws we take for granted, because sometimes the universe winks at us through a pot of freezing water. The silent depths of space are not as empty as they seem, even for our own robotic explorers. For decades, two pioneering spacecraft, Pioneer 10 and Pioneer 11, carried humanity's greetings into the interstellar void. As they journeyed beyond the orbit of Pluto, scientists tracking their precise trajectories noticed something deeply puzzling. Both spacecraft were experiencing a tiny but persistent deceleration, a slight but constant pullback toward the Sun that could not be explained by any known force of gravity or planetary influence. This was the Pioneer Anomaly, a minuscule drift that defied our models of the solar system. The discrepancy was incredibly small, less than a billionth of the acceleration we feel from Earth's gravity, but in the precise realm of orbital mechanics, it was a glaring red flag. For years, this anomaly fueled speculation about unknown physics, perhaps a hint of dark matter's local effects, or even a subtle flaw in Einstein's theory of gravity itself. It was a whisper from the void that our map of reality was incomplete. The mystery was eventually solved through meticulous detective work, tracing the effect to an unexpected source, the gentle, anisotropic push of thermal radiation. Heat radiating unevenly from the spacecraft's nuclear power sources acted like a faint photon rocket, slowly breaking the probes. This resolution was a triumph of careful science, yet the episode remains profoundly instructive. For a long time, that unaccounted-for drift existed as a genuine glitch in our understanding, a placeholder in the equations marked unknown. In a simulated reality, such anomalies are particularly telling. They resemble rounding errors in a vast calculation or slight miscalibrations in a physics engine. When a video game character moves, their trajectory is calculated frame by frame based on the game's internal laws. If there is a tiny error in that code, perhaps in how friction or gravity is applied, the character might drift imperceptibly off course over long distances. The Pioneer Anomaly felt like that, a hint that our cosmic simulation's gravitational model might have had a parameter slightly off, a bug so small it only manifested in the deepest, quietest stretches of the system where no other forces could mask it. While this specific case was solved, its legacy is a powerful reminder. Our grasp of physical law is built from observation, and sometimes the observations contain whispers we do not yet understand. The next unexplained drift of a distant spacecraft, the next tiny orbital discrepancy around a distant world, could be mere thermal noise, or it could be the first crack we see in a much larger facade. It encourages a posture of cosmic vigilance, where even the smallest inconsistency in the data is a clue waiting to be read, a potential signpost pointing toward the deeper architecture of everything. Watching something closely might actually prevent it from ever changing. This strange behavior is captured in the 18th glitch, the quantum Zeno effect. Named for the ancient Greek philosopher Zeno of Elea, who famously argued that a flying arrow is motionless at every instant, this is not just a philosophical puzzle. It is a real, measurable phenomenon in the quantum world. Experiments have shown that if you observe an unstable quantum system, like an atom poised to decay with relentless frequency, you can essentially freeze it in its initial state. The constant act of measurement resets its internal clock, preventing the natural evolution that would have occurred if it had been left alone. It is as if the system, under the unblinking gaze of an observer, cannot find a moment to transition, forever held in place by the spotlight of attention. This effect provides a startling physical basis for an old idea that observation is not a passive act. In the quantum realm, to look is to touch, to measure is to meddle. The Zeno effect suggests that our reality does not simply unfold on a predetermined track, independent of us. Instead, it updates, recalculates, and presents itself in response to our interrogation. The simulation hypothesis offers a compelling reason for this. In any complex program, monitoring a specific variable or process in real time is computationally expensive. If the system is being watched continuously, it might be more efficient to simply pause or dramatically slow that particular calculation until the observation stops, then resume the process in the background. Think of a character in a game standing perfectly still while you open your inventory menu to examine an item, the world around them freezing to conserve processing power for your focused task. The quantum Zeno effect could be a microscopic version of this optimization, a sign that the simulation conserves resources by not rendering changes that no one is around to witness. This glitch profoundly blurs the line we thought separated the observer from the observed. It moves us from the philosophical implications of the double slit experiment into a realm of tangible influence. If watching a quantum system can lock it in place, what does that say about the power of focused attention in our own lives? While the effect is most dramatic at the atomic scale, it invites a deeper question about the nature of consciousness and control. Are we merely reading the data of the universe, or does our persistent, directed awareness play a role in writing it, however small? The quantum Zeno effect transforms observation from a window into reality into a potential tool, a subtle force that can, under the right conditions, hold a piece of the world in stasis. It whispers that the relationship between mind and cosmos might be far more interactive and far more mysterious than we ever dared to believe. The universe we can see is a ghostly afterimage, a faint shimmer on the surface of a vast and invisible ocean. Over 95% of everything that exists is made of substances we cannot detect, touch, or even comprehend. This is the profound enigma of dark matter and dark energy, a glitch so massive it rewrites our entire cosmic story. We observe galaxies spinning so fast that the visible stars and gas within them should be flung into the void, yet they hold together, bound by the gravitational grip of something unseen, dark matter. Meanwhile, the fabric of space itself is stretching apart at an accelerating rate, driven by a repulsive force we call dark energy. These are not minor mysteries. They are the dominant forces shaping our cosmos, and they remain utterly invisible to every instrument we have. They are the hidden variables in the grand equation of reality. From a simulation perspective, this makes a startling kind of sense. In any complex virtual environment, the world rendered for the user is only a small fraction of the total data being processed. The lush forest you explore in a game is not the entire program. It is the graphical output generated by a vast, underlying engine handling physics, artificial intelligence, and world-state calculations. What if dark matter and dark energy are not physical substances in the traditional sense, but artifacts of that underlying architecture? Dark matter could be the gravitational scaffolding code, the invisible framework the simulation uses to keep galaxies and clusters properly structured without having to render every single particle in high definition. Dark energy might represent the parameters controlling the expansion of the simulation's spacetime itself, a background setting that determines the rate at which the cosmic canvas is stretching. They are not things within the simulation so much as they are features of the system running it. This idea transforms our cosmic ignorance into a potential clue. The fact that 95% of reality is hidden from us could indicate that we, as observers, are only granted access to a limited rendering. We see the beautiful graphics, the planets and stars, but not the complex code that maintains the stability and expansion of the entire system. Some theorists, like philosopher Nick Bostrom, have even suggested these dark components could be the result of approximations or shortcuts in the cosmic calculation, places where the simulation uses a simplified model to save processing power, and these simplifications manifest as mysterious forces in our observable reality. This glitch challenges us in the most fundamental way to look beyond the illuminated stage and consider the unseen machinery behind the curtain. Our relentless search for dark matter particles might be like a character in a video game trying to find the computer's central processing unit within the game world itself. It is simply on a different layer of reality. The dark universe whispers that what we perceive is not all there is, that the true nature of existence may lie in the invisible code, not the visible creation. Our own technological trajectory may be the ultimate clue to the universe's true nature. As we stand on the brink of creating artificial intelligence that rivals our own and computing power that expands beyond our imagination, we are quietly building the tools to become creators of entire realities. This is the concept of the technological singularity, a point futurists like Ray Kurzweil suggest is not only possible but perhaps inevitable, where technological growth becomes uncontrollable and irreversible, leading to a future unfathomable to current human minds. Within that future lies the capacity to generate not just complex models, but fully immersive, conscious simulations, populated with minds that believe they are as real as we believe ourselves to be. This 20th glitch creates a profound, recursive loop. If it is possible for a civilization to reach such a point, and if such a civilization would likely run countless simulations of its own ancestors or of entirely new worlds, then the sheer number of simulated beings would quickly dwarf the number of original, biological ones. Statistically, any conscious entity is far more likely to be in a simulation than in base reality. Therefore, if we are on a path to become simulators, it is overwhelmingly probable that we are already inside a simulation created by a previous iteration of intelligence. Our drive to create artificial worlds mirrors the very process that may have created ours, suggesting a cosmic pattern, a nesting doll of realities. This transforms the simulation hypothesis from a philosophical thought experiment into a potential prediction of our own future. It encourages a startling perspective that our most advanced technological endeavors are not just shaping our future, but are echoing the architecture of our past. The act of building a conscious artificial intelligence or a detailed virtual universe is not merely progress. It is a form of cosmic introspection, a way of reverse engineering the principles that may govern our own existence. It implies that consciousness itself might be a substrate-independent phenomenon, a kind of software that can run on different hardware, whether biological or silicon, in base reality or in a simulation. This final glitch ties our quest for knowledge directly to our existential condition. As we push the boundaries of what we can create, we are simultaneously uncovering clues about what we might be. The technological singularity is not just an event on our horizon. It is a mirror held up to the nature of reality itself, asking us what it means to be a creator when we may also be the creation. This cascade of glitches forces us to confront a single, overwhelming question. If our reality is a construct, then what is its purpose, and who or what is running the simulation? The technical clues lead us into a profound philosophical maze where our most cherished beliefs about existence are put to the test. If we are characters in a program, do our choices truly matter? Does our suffering have meaning or our joy have weight? The simulation hypothesis does not just challenge physics, it dismantles the entire metaphysical framework of our lives. Thinkers like Nick Bostrom, who framed the statistical argument, and figures like Elon Musk, who has publicly endorsed its likelihood, force us into this uncomfortable territory. They highlight that this is not merely a scientific puzzle, but a complete redefinition of what it means to be real. One possibility is that we are part of a grand experiment. Perhaps a higher order of intelligence is running countless iterations of civilizations to study cosmic evolution, the rise of consciousness, or the outcomes of different historical paths. In this view, our lives are data points, our societies are test cases, and every war, every discovery, every act of love or cruelty is recorded for analysis. Another possibility is that we are entertainment, a form of immersive storytelling or recreational experience for beings whose reality is utterly foreign to our own. Our entire history, with its drama and struggle, could be a narrative crafted for an audience we can never perceive. This can feel deeply unsettling, as if it diminishes our significance to mere lines of code in someone else's project. Yet there is another way to see it. If this is an experiment, then our actions are not meaningless. They are the very point of the exercise. Our capacity for creativity, for compassion, for scientific inquiry, could be the variables the simulators are most interested in observing. Our free will, whether it is an illusion granted by sophisticated algorithms or a genuine feature of conscious software, becomes the engine of the study. This perspective does not erase morality, it potentially heightens it. If we are being observed, then how we treat one another, how we steward our world, and the legacy we build could be the most important data we generate. It reframes life not as a random accident in an indifferent universe, but as a performance with cosmic stakes, where every decision contributes to the outcome of the simulation. The hypothesis ultimately challenges us to find our own meaning within the mystery. Whether we are base reality or simulation, the experience of consciousness, the ache of beauty, and the search for truth are undeniably real to us. This realization can be liberating. It invites us to live with greater curiosity, to treat our reality as the precious and possibly unique artifact that it is, and to remember that even within a crafted world, the love we feel and the connections we forge are no less profound. The final glitch, then, is not in the cosmos but in our own perception. The greatest evidence for or against the simulation may forever lie in how we choose to live within the question itself. The journey through these 20 glitches leaves us not with a final answer, but with a transformed perspective. From the double-slit experiment's watchful particles to the silent, dark expanse that fills the cosmos, each anomaly feels like a loose thread in the fabric of reality. Pull on any one of them, and the entire tapestry of a purely physical, accidental universe begins to unravel. Together, they weave a compelling pattern, one that suggests our existence is governed by rules that look less like immutable laws of nature and more like the elegant, efficient processes of a computational system. This is the profound invitation these glitches extend, to fundamentally rethink what we are and where we are. It challenges us to see the universe not as a cold, indifferent machine, but as a dynamic, possibly constructed, information-based reality. Yet, here is the most crucial realization of all. Whether we are beings in a base reality or sophisticated code in an ancestor simulation, the experience itself does not change. The awe we feel gazing at the stars, the curiosity that drives us to probe quantum foam, the connections we forge with one another, these are the undeniable textures of our existence. The pursuit of knowledge and the capacity for wonder are not diminished by this hypothesis, they are amplified. They become the very tools through which we might one day understand the architecture of our own cage. So reflect on these ideas, let them sit with you, Look at the world around you, at the way light falls through a window or the way a stream branches like a fractal, and ask yourself, what do I see? A purely material accident or the signature of something deeper? Share your thoughts in the comments below. Do you find the evidence compelling? Do you believe we live in a simulated universe, or does another explanation speak to you? If these mysteries captivate you, subscribe for more deep dives into the enigmas of space and existence. Keep questioning, keep wondering, because the search for truth is a journey without end. And as we have seen, sometimes the biggest clues about everything are hidden in the smallest, quietest glitches of all.